Hey guys, so back by popular demand, let's go ahead and do another video. So this is for Chapter 5, or anyone interested, or for Chem 204 students for Jacksonville University. But we're going to go over specific heat capacity. Maybe how to calculate specific heat capacity, or how to calculate any of the other terms that are in there. So let's start by defining what this equation is. So this is the heat represented by lowercase q, and it's usually represented in joules, right? This is the mass, and it's going to be represented by grams. This is the specific heat capacity, and that's going to be represented by joules per gram degrees Celsius, which is actually equal to joules per gram times Kelvin. Now that may seem a little strange to you, but if you were to increase the temperature of a room by 1 Kelvin or 1 degree Celsius, it's the same thing. They're clearly numerically they're different, but the change in temperature for degree Celsius or Kelvin, it's the same thing. So this is usually the one that people tend to go for. This is usually the one that I go for. This is usually how I word it, but they're interchangeable for only this situation. And delta T is the change in temp, and it is TF, so final, minus initial, and it's going to be in units of degrees Celsius, or Kelvin if you happen to have Kelvin over here. Again, it doesn't matter because the intensity of 1 degree Kelvin is equal to the intensity of 1 degree Celsius, and I know I said degree Kelvin. 1 Kelvin is equal to the intensity of 1 degree Celsius. So, with that being said, let's go ahead and look at, I have 2 sample problems for this video. So let's look at one. A 22.8 gram sample of a metal absorbs 212 grams of heat. The temperature of the sample raises from 22.1 to 42.7. What is the specific heat? So let's start off by defining what we know. Do I know Q? Do I know M? Do I know the specific heat? Do I know delta T? This approach of defining the terms on the side and then plugging them in usually helps people out. So do I know Q? Do I know the energy, the heat that it absorbed? Yes, 212. And is it in the correct term? Yes, it's in joules. So I can plug it in. It's ready to go. How about mass? 22.8. Do I know specific heat? Actually, I don't. That's what I'm trying to find, right? Do I know delta T? Well, I have 2 temperatures, but I don't know delta T right yet. I have to actually find that, don't I? So I have to do final minus initial. If it started at 22.1 and it raised to 42.7, this is my final, this is my initial. So it's going to be T final minus T initial, which would be 42.7 degrees Celsius minus 22.1 degrees Celsius, which I will go grab a calculator for the next part, but I believe that would be 20.6. Do a quick double check in my head. Yep, that's going to be 20.6. That's the change in temp. These are all in the correct units. Degrees Celsius, grams, joules, so they're ready to be plugged in, right? So go ahead and just plug and chug. So Q, which is 212 joules, equals mass 22.8 grams times specific heat, I don't know that, right? Times my delta T, which is going to be 20.6 degrees Celsius. So I'm going to run and grab a calculator, unless I have one handy. Let me see. Hold on one second. Alright, so I'm back now. So all we have to do is solve this problem. So essentially we're going to be multiplying these 2 numbers and then dividing it into 212. So I'm just going to do this fast. I'm going to take 212, I'm going to divide it by whatever 22.8 times 20.6 is. The specific heat capacity is 0.451. And what are the units? Joules per grams times degrees Celsius. And so let's move on to a second one. A second example I have set up. This one says, well, what if we have a sample of iron? It absorbs a certain amount of heat and it causes the temperature to raise a certain amount. We know the specific heat of the iron. What's the mass of the sample? So it's very much a similar idea. So let's go ahead and define our terms. Or we could even rewrite the equation. Q equals M times C times delta T. Do I know my Q? I sure do. 95.1 joules. Do I know my mass? No, actually, that's what I'm going to be looking for. Do I know my specific heat capacity? Yes, 0.450 joule per gram times degrees Celsius. And do I know my delta T? No, not yet, but we can calculate it super quickly. It's going to be my final minus the initial. So it's going to be 41.7 degrees Celsius minus 25.0 degrees Celsius. So let's go ahead and calculate that real fast, because I will not do this in my head. I won't do that to you guys. That's 16.7 degrees Celsius. So I can go ahead and plug it in, and I just solve for my M, right? So 95.1 joules is going to equal M times 0.450 joule per gram degrees Celsius times 16.7 degrees Celsius. Now if you take a second to step back, you'll notice that when we multiply degrees Celsius and degrees Celsius, the degrees Celsius here is on the bottom of the fraction of the ratio. These two will cancel out. And then when we divide everything over, this joules is going to cancel out with this joules. So the only thing left with is grams when it comes over here. So what we can do is we can multiply 0.450 times 16.7. So I get 7.515 times M, and that equals 95.1. I'm not using units because I'm just doing the algebra portion of this right now, right? Scooch up. And so then I take 95.1 and I divide it by 7.515, and I get 12.6. So mass is equal to 12.6 grams. That's how big of a chunk of iron that we have. So I do hope that this helped break it down, how to do specific heat capacity, the very simple problems of heating up a substance, and you can determine any of the other factors in here, as long as you know how to define what you have and you plug it in and see what you're missing. Good luck.